is there. However, we don't want to overwhelm our hospitals, so if you're exhibiting moderate symptoms, please call your primary care physician first before visiting the emergency room. Las Robles Hospital will be sponsoring a blood drive. That's this Wednesday and Thursday at 2190 Jans Road. It will be from 7 a.m. to 9 p.m. You can visit bloodforlife.org for information on that program. Food Share, which is our county regional food bank, will be delivering food to residents of Thousand Oaks on April 2nd. You can visit foodshare.com/COVID-19 for information on that program as well. And naturally, we want our seniors to be protected during this tough time. Senior Concerns is doing a great job with Meals on Wheels. If you want to help, go to seniorconcerns.org where you can donate or volunteer your time to make these deliveries. Ladies and gentlemen, the city is running well. Police and fire are there for your protection. We have a virtual library at your disposal, and you may notice that some construction projects are still running throughout the city. If you do have any concerns or you need our help, please feel free to call us at any time. We're there for you. And in the meantime, let's exercise our civic duty. Let's stay apart. Let's use distancing. It's the only way to stop this virus. We're in this together. I wish you all well, and I'll be back with another update shortly. Thank you very much.
Funding for this program is provided by Annenberg Media.
Most of us learned at an early age how an apple falling from a tree inspired Isaac Newton to describe how the universe behaves by certain predictable rules. But what about when the universe doesn't behave so predictably? Can mathematics explain the often unpredictable behavior of the physical world? Everything from the weather to the way a baseball travels through the air. Welcome to Chaos Theory.
Jake's fastball's coming in about 94.
Yep.
An object at rest will remain at rest
Unless acted upon by an external and unbalanced force. Newton on your mind again?
Yep. I've always been partial to his first law of motion.
Uh-huh. Yeah, a lot of forces act on a baseball. Gravity, friction, turbulence.
Turbulence?
Mm-hmm. Knuckleball. Some things you just can't predict.
Still, every action has a reaction.
Pops and Red are discussing an age-old dilemma. Why in nature some things like a baseball can behave both predictably and unpredictably. And it's an exploration that began in earnest and one that used mathematics with Isaac Newton and his apple in the late 17th century. Newton's revelation about gravity led him to define a set of rules about how the physical world operated, which he published in 1687. His laws were in fact so precise that they seemed to describe the world as perfectly balanced, behaving like clockwork. Newton's laws would influence all the sciences, as well as the arts, religion, and philosophy for centuries to come, essentially framing how civilized man understands the universe. The philosophical movement that arose from Newton's mathematical concepts came to be called determinism, the belief that future events are necessitated by past and present events, in combination with the laws of nature. Now, some scholars even took this one step further, suggesting that once the initial conditions of the universe were set, the rest of history was inevitable. This is one of those examples where a little bit of mathematics in the wrong hands can be dangerous. But on the other hand, the ideas that there's a clockwork universe or that there's a regularity to the world as described by Newton's laws is in fact something that we know to be true for much of physical phenomena. So, with his three laws of motion, the laws of inertia, acceleration, and reciprocal actions, Newton was the first to mathematically describe how an object's motion through space and time can be calculated by adding up the infinitesimal changes in its path. In other words, Newton showed us how to use mathematics to predict an object's motion from instant to instant, given such quantities as acceleration, mass, and gravitational pull. Newton's ideas were revolutionary, an entirely new way of thinking about the universe. After all, he showed us how we can use the mathematics of differential equations to predict the future, differential equations as a mathematical crystal ball. Let's look at a simple example. Suppose we have an object X traveling around an object Y solely under the influence of gravity. Then we know exactly where X will be in space 10 seconds or even 10,000 years from now. Newton's theory efficiently described the interactions of what we would call a two-body system, answering the question, what occurs when the forces of two masses affect each other? Now we see the power of these ideas some 200 years later with the advent of more powerful telescopes. At that time, astronomers noticed that some planets were not following the perfect Newtonian elliptical orbits, especially the planet Uranus. So they theorized that its orbit must have been upset by some other body. And then using differential calculus, they were able to actually calculate the orbit of an unknown orb. The mathematician said, "Point your telescope here and you will find it." And so in 1846, there it was. Neptune became the first planet to be discovered based on mathematical prediction rather than mere observation. The late 19th century was in fact alive with such scientific triumphs, and royal prizes were offered for solutions to the most challenging mathematical problems. One such challenge was introduced by the King of Sweden in 1888. He offered a prize to anyone who could solve the so-called three-body problem. In layman's terms, the king asked, does Newton's two-body solution, the simple elliptical motions of a single planet around a massive sun, can we do the similar prediction for more than two bodies? One of the greatest mathematicians and scientists of all time took up the king's challenge, Jules-Henri Poincaré. Now, Poincaré tried to find a closed-form solution to the famous problem using those differential equations. Again, essentially looking for a formula like one for an ellipse to describe the motion of several planets, all under the influence of gravity. Although Poincaré didn't succeed, he came close enough that the king awarded him the prize anyway, because his explorations had made a significant contribution to classical mechanics, besides adding a lot of mathematics. However, when a referee asked for a clarification, Poincaré discovered an error, and the great mathematician went back to the drawing board. Unable to solve the problem as it was originally posed, Poincaré made up his own. Will the solar system always stay together, or will it fall apart? What Poincaré discovered was that for more than two bodies, certain initial conditions could lead to chaos. You see, with two bodies and Newton's equations, basically only two things could happen. Either the two objects could move apart to infinity, essentially like a meteor passing by the planet, or we could get the familiar old periodic solutions of one planet orbiting around another one. And most importantly, changing the starting position slightly wouldn't change the behavior. But add some more objects to the situation and suddenly all bets were off. Other wild, non-periodic behaviors could happen. And moreover, slight changes in the starting positions could have very different long-term effects. Although roughly, the bodies would still move in approximately the same region of space. Poincaré's discovery was astounding, but even more, the way in which he made this discovery was at least as important as the discovery itself. His epiphany was that the system of equations could be approached visually. To understand what Poincaré did, we have to understand a bit more about the problem. In classical mechanics, an object's position is recorded using its location in 3 dimensions, the so-called x, y, and z coordinates. When that object is moving, its velocity along each of these axes is also noted: velocity x, velocity y, and velocity z. When a second object is added to the system, 6 more variables must now be calculated. As additional objects are added, tracking all of the variables can be completely unwieldy, especially if the calculations are difficult. Still like clockwork, just a lot of moving parts, what mathematicians call a deterministic dynamical system. What Poincaré saw was that if we look beyond the numbers that govern the orbits of the planet, we would find that the entire system could be viewed as a single point, moving through a multidimensional space of very high dimension. We now call this phase space. And what the picture told him was that the system as a whole would behave unpredictably, like a leaf floating down a stream. Poincaré's revelations put a crack in the foundation of Newton's clockwork universe and paved the way to a theory of chaos. But no one would really explain the unpredictability that Poincaré's calculations hinted at until midway through the 20th century, when one man stumbled on an explanation while using computers to examine a problem much more complex than 3 bodies moving through phase space: weather patterns on the planet Earth. At MIT in the early 1960s, Dr. Edward Lorenz built a simplified mathematical model of the way air moves in the Earth's atmosphere. Working with a 12-variable computerized weather model, Lorenz repeated a calculation involving a numerical representation of a slightly shifting wind condition. To save computation time, he began the simulation in the middle of its course, but entered the data by rounding off the original 6-digit variables to just 3 digits, an adjustment of just 1/1000th from the original setting. But to his surprise, the weather that the computer predicted on this new run, using these slightly different intermediate values, was completely different than his earlier simulations. Lorenz expected that the minuscule difference would have practically no effect. By iterating this slightly altered calculation, Lorenz realized that minute variations in the initial values in his weather model could result in widely divergent weather patterns. Remember, Newton showed how an object's motion through space could be predicted by calculating the infinitesimal changes in its path. Now Lorenz was showing that for certain equations, an infinitesimal change in the data could end in a highly unpredictable result. That's what we mean by sensitive dependence on initial conditions. The error, the distance between the 2 trajectories, grows exponentially fast. The fact that small changes in initial conditions produce large changes in the long-term outcome is the trademark of a chaotic system, and it's called sensitivity to initial conditions, or sensitive dependence. And this process of iteration can be thought of as an amplifier or a mechanism that reveals the sensitive dependence. Using the computer, which made it possible to rapidly repeat and accumulate the infinitesimally small changes over and over again, Lorenz was able to actually chart this sensitivity. The resulting graph, called the Lorenz attractor, is in fact a phase space representation of this simplified model of the weather. The graph's similarity to the shape of a butterfly caught on as a way to illustrate the concept of sensitive dependence. So it's a magical coincidence that we explain this by sometimes saying that a butterfly flapping its wings in China might cause an infinitesimal change in wind current that could lead to a hurricane in Florida several months later. The butterfly effect.
First butterfly of the season. Kind of warms your heart, don't you think? Hey, did I ever tell you about how chaos theory is connected to heart dynamics?
Think it's gonna rain?
Feels humid, all right. Good air for a knuckleball.
It wouldn't have anything to do with turbulence, would it?
Well, a ball that spins, say a fastball if thrown correct, can take a more predictable Newtonian path as it moves through the air.
But a ball that doesn't spin?
Well, that's where celestial mechanics meets chaos theory.
Baseball and mathematics, two great American pastimes. So we're here today with Steve Strogatz, author of the book Nonlinear Dynamics and Chaos, and also a professor of theoretical and applied mechanics at Cornell University. And Steve's going to help us make sense out of chaos on the baseball field. Steve, ready?
Hey, you know, your friends Pops and Red are having a pretty interesting conversation out there.
They're quite the grizzled old philosophers.
So the thing about a knuckleball, you know, is that the pitcher grips it with two fingers in this flat part here. And the trick is to throw it so that it has very little spin. And what happens then is that the airflow around the pitch starts to create vortices, little whirlpools of air behind the ball.
So it's actually almost pushing the ball
Yeah,
forward,
sort of
is that
pushing.
right?
Well, I mean, mainly the ball has its own inertia carrying it forward, but these whirlpools do, if they're in the wake of a knuckleball, sort of push it around in a funny and unpredictable way, whereas a fastball, which would have much more spin, has a much more predictable wake, and it leads to a pitch that's more predictable, except, of course, it's fast.
I mean, so a wake, so just like a boat moving through the water, you see something behind it, and that's the wake, and that's exactly what this is doing in the air. And depending on whether or not it's spinning, you get different wake patterns in the back. Is that right?
That's right. And so the chaotic wake behind the knuckleball is more turbulent, and it makes the pitch less predictable in the sense that the next time the pitcher throws it, even if he just changes the angle a little bit of release or the speed, it'll end up looking like a totally different pitch.
So that's an example of this sensitive dependence on initial conditions that we're going to be hearing
Right, it's
about.
chaos at work on the baseball field. Just a tiny change in the pitch makes a big change by the time it crosses the plate.
These slight changes with the knuckleball are going to affect, well, very different paths that still end up at home plate or somewhere around home plate.
Right.
So is that...
Yeah, that's
right.
the idea. And so what we want to try to understand a little better is how is it that something that starts like a tiny difference, how can those tiny differences get amplified and grow exponentially fast, leading to very different outcomes?
Right.
And so it seems like one way that we might want to look at it is what we're showing here on the screen now. We could take a look at just doing this with numbers, okay? Not with...
Very simple numerical
just a
examples
number
of
line
these
that you've been
complicated
using.
physical phenomena, right?
Right.
Yeah.
So let's just focus on numbers, and we'll do a certain operation on the numbers, which is to...
So just numbers between 0 and 1. We only have that piece of the lines.
Yeah,
line
so
there.
not the whole number line. Just start from 0 to 1 and pick some number in there. Let's say 0.632.
Okay.
Okay, and you could imagine that there's more digits after that if you want. But let's just 0.632, and then we multiply by 10. This is the operation we're going to do. And so then we would get the number 6.32.
Right.
And what I want to do next is an operation that a mathematician calls mod 1, which means just drop off the number before the decimal point.
Okay.
So 6.32 would then become just 0.32.
Mod 1.
Okay, now what I want to do is compare that to what would have happened if we had originally started with 0.633, making only a difference in the 1,000th place, right?
Yep.
I mean, in science, normally, if you have something that's good to 3 digits, you'd say that's pretty good.
I'm done.
Okay, yeah. But watch what happens if we do our operation on 0.633.
Okay.
Then we multiply by 10, we get 0.33.
Right, we multiply by 10, we lop off the integer.
Yes, but that differs from our original number.
Right.
Not in the thousandth place, but now in the hundredth place.
Right.
We've amplified the error, the difference, by 10.
Right.
Okay, and if we did this one more time...
Right, so we're doing both of them. We multiply them both by 10, we lop off the integer, and now we compare. And now they differ just in the tenths place. So we have another multiple of 10 in the error.
Yeah, so that's the thing, that the difference between these two outcomes is growing by a factor of 10. It's growing exponentially fast as we go forward in time. And that's what happens in chaotic systems. But you might think, and so this is the other interesting point, why we need the mod, that the error, if it kept growing exponentially, that would be like one of the baseball pitches going out of the stadium. That doesn't happen here, because the mod keeps things bounded to always lie
always
between
on our
0
little
and 1.
segment here.
Yeah, always stays in our segment eventually. So things can get far apart, but not too far apart.
Yes.
And that's what we see in chaotic systems too.
So this is an interesting point that, again, people think of chaos as, totally unpredictable, uncontrollable.
Yeah, that's right. And the way the mathematicians use chaos, it may be not the best word for the subject in a way, because what we should think of is that there's a whole spectrum of disorder. If we keep sort of like raising the heat, to wilder and wilder behavior, then you would start to see something like turbulence, where it's complicated not just in time, like chaos, but also in space. There's a counterpart to the turbulence that arises in living things. It would really be a matter of life and death, which is complicated behavior in your own heart in space and time that we call fibrillation.
So fibrillation is actually turbulence in my heart.
It's a kind of electrical turbulence. Instead of the organized rhythmic flow of electricity that triggers the ventricles to beat properly in sync, you find that you start to get something like electrical vortices, electrical whirlpools on the heart, causing different parts to beat at different times. You get uncoordinated beating, and no blood gets pumped. And when people die suddenly in a matter of minutes from cardiac arrest, that's what's happening at the electrical level. So mathematicians nowadays are just starting to work with cardiologists to try to figure out this most deadly arrhythmia using modern-day versions of chaos theory, the cutting edge of chaos.
I see. So a beautiful and important intersection of mathematics and medicine. Well, Steve, thanks a lot. This has been a really exciting tour of chaos in all sorts of different venues, and I appreciate the tour.
Sure. Thanks. My pleasure.
So now we're going to look a little bit more closely at the use of chaos in cardiac dynamics. When mathematicians talk about chaos theory, what they're talking about is mild wild, poised between metronome regularity and the craziness of turbulence. Scientists have begun to explore chaos for such practical applications as the treatment of heart disease. Chaos is giving us a lot of new insight into heart dynamics, helping us understand the arrhythmias that can, in the worst cases, lead to sudden cardiac death. More than 300,000 people in the United States die of cardiac arrest every year. Most attacks are brought about by an abrupt change from rhythmic pumping of the heart muscle to spasmodic convulsions. Scientists discovered that the unstable palpitations, known as cardiac fibrillation, are a form of chaos. Like all chaotic occurrences, it isn't completely random. The heart can become arrhythmic because of stress, an injury, or some abnormality in the muscle tissue. The electronic impulses of the heart begin rotating in a kind of spiral wave. This rotating disturbance can travel, its chaotic impulses circulating through the heart tissue. It may also break up into a small number of added spiral waves, all rotating and diverging, causing the system to destabilize. By using the math of chaos, researchers were able to calculate how to give small electrical pulses to test animals, and then eventually humans. These pulses induced premature beats, which cardiologists were able to use to coerce the heart tissue back into a healthy rhythm. Scientists have yet to utilize chaos in specific medical applications, but perhaps the theory will someday lead to better anti-arrhythmia drugs, gentler defibrillators, and other beneficial technologies. Beyond heart dynamics and computer animation, scientists and mathematicians use chaos to explore evolutionary biology, economics, population growth, artificial intelligence, gaming and probability, even making more efficient fuel injectors. But perhaps one of the most interesting explorations is one that takes us again into outer space.
The interplanetary superhighways is a network of ultra-low energy orbits generated by the 5 Lagrange points that connect the entire solar system. And it explains how things can move back and forth using chaotic dynamics. I'm Martin Lowe. I work as a mission designer and designing trajectories for space missions at JPL. The very specific branch of mathematics that we use to study the interplanetary superhighway is called dynamical systems theory. It gives us a very different picture of the solar system. Instead of just isolated planets in near circular orbits around the sun, this interplanetary superhighway concept says that all the planets, the moons, the asteroid belts, the comets, the Kuiper belt, they're all actually dynamically connected and linked. So even though you don't see the orbits connecting them, there's a web underneath. Lagrange points are what I call the seeds of the interplanetary superhighway. There are locations where all the forces, the gravitational forces, are balanced with the rotational forces, so that if you put a particle there, it would just remain there. But if you just have the slightest motion on it, breathing on it, would cause it to drift away. It's as if you're starting on street number 1 and then you go down, it will take you to one place. But if you start on street number 2, not only will it take you to a different place, but it'll be actually to another city. So in our case, it could be actually to another planet. Starting from these Lagrange points or the equilibrium points, they generate families of periodic orbits. So these are orbits that close on themselves, and they surround the Lagrange points, and they get bigger, bigger, and bigger. And what happens is that these are very special types of periodic orbits that are very sensitive, or people call them unstable. But this sensitive dependence is really the definition of chaos. The very first mission that used this type of very sensitive orbits, and it was called the IC-3, International Sun-Earth Explorer 3, was launched in 1978. By using the sensitive dependence on slight changes, it was able to reorient itself, move away from the L1 Lagrange point, and actually go to study a comet. And so it's this type of sensitivity and energy savings that makes these orbits very, very powerful. Here we are in the JPL Space Museum, and behind me is a life-size model of the Galileo spacecraft. What's really exciting for me is that even though the original design used very classical theories to come up with a trajectory, we now can show that it's actually following the pathways of the interplanetary superhighway. In terms of the future research on the concept of the interplanetary superhighway, there's really two sides. From a scientific point of view, by understanding these pathways and mapping them out, it'll help us to understand how solar systems form, how the transport of material that builds life comes to the Earth. On a second vein, is more practical for humans, is that it will help us to find ways to fly cheaply from A to B. It might help us to deflect, detect, and even perhaps capture rogue asteroids that might otherwise hit the Earth.
Oh, you see that?
Oh, you mean that shooting star?
Yeah, beautiful.
Could have come all the way out from the hyperbelt. Caught the interplanetary superhighway.
I know. You and your Lagrange tubes. Bunch of convoluted mathematical mumbo-jumbo, if you ask me. Chaos theory. Give me old Isaac Newton anytime.
You know, I don't think the weather has anything to do with clockwork.
You wouldn't be suggesting that we're going to get rained out on account of some butterfly flapping its wings in China, would you?
You mean the butterfly effect?
Yeah.
A butterfly flapping its wings in China, causing a hurricane over Florida, might be a stretch, but mathematically, well, as we've seen, anything's possible. And maybe that butterfly is the right metaphor for mathematics and mathematicians. Small discoveries over time, as well as the big ones, amplified through history, done by some of the greatest thinkers of all time. Pythagoras to Euclid, Newton, Poincaré, Lorentz, and countless others whose journeys travel amazing intellectual trajectories through history. And with chaos, we've just begun to explore the unpredictable, on our way to perhaps discovering other superhighways of knowledge that might someday lead us to the end of the unknown.
information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.com.
We know that we're asking Americans to do a lot right now. So we're asking everyone to be selfless for others so that we can protect those who are most susceptible to this virus.
A question I often get asked is, why should young people care about the spread of coronavirus? Well, we know that people with underlying medical conditions over the age of 60 are at highest risk, but they've got to get it from somebody.
Social distancing is really physical separation of people.
It's what we refer to when we ask people to stay at least 6 feet apart.
Not going to bars, not going to restaurants, not going to theaters where there are a lot of people. It all just means physical separation so that you have a space between you and others who might actually be infected or infect you.
We all have a role to play in preventing person-to-person spread of this disease, which can be deadly for vulnerable groups. For more information on how you can social distance, please go to coronavirus.gov.
Annenberg Media.
Why can't I see colors in a dark room? Why can't I see anything if there isn't any light? Do all animals change color?
Welcome to Shedding Light on Science. I'm Anita Greenwood, a science educator at the University of Massachusetts Lowell.
And I'm Christine Jones, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics. Later in today's session, we'll be joined by our colleague, Dr. Camille Wainwright at Pacific University. In this series, we've seen that light is made of photons of differing amounts of energy. In Workshop 3, we talked about visible light, as well as light that's not visible to us. We looked at how we detect light that we can't see, like radio photons that open garage doors, and infrared photons that we feel as heat on our skin. And I talked to you about my work with X-ray telescopes.
Today, we'll focus on detectors that are familiar to all of us, our eyes. You may not usually refer to your eyes as detectors, but that's exactly their function, to detect the presence of visible light energy.
Compared to the whole spectrum of light, the region that our eyes can detect, the visible light region, is quite small. It's the interaction between visible light, our eyes, and our brain that we'll explore today.
Let's begin by examining how children believe we see objects. We asked Michelle Sullivan's 4th grade children in Worcester, Massachusetts, to draw posters to explain how they think they see objects. How do you think children in your class would explain how they might see a tree in a field?
Here's my poster, and
shows this little boy reading a book, and he's thinking about what he said, like that he couldn't see without light. And this boy is trying to figure out a math problem, and it shows him looking at the object, it coming back into his brain upside down, and then projecting out again, upside down, right side up. And over here, it says facts. It means 5 actual causes to seeing. All the colors you see come from 3 colors, red, blue, and yellow. Number 2 is light is a different color. Number 4 is you see from light. Number 5 is light makes colors.
The light entered to our eyes, but it doesn't enter correctly. The picture that we are seeing enters upside down, and then it goes after in our head, and then it comes again correctly, and so we can see. Remember that we can't see without light, and we can't see the colors in a dark room because there's no light. The light is an important resource for the earth.
I drew a car and I have an eye looking at it, and these are seeing lines, but there you don't like when you're looking at something, it does, if someone's looking at you, they don't see seeing lines, it's invisible. And I said they're looking at the car, and I wrote seeing lines are colored light that we can see right away, and in the air there are colored particles that help us see the light and color, and it helps us see because if we don't have any light, then we couldn't see anything. Well, a lot of people think we can see in the dark, but all we will see is black and white, and we need like either seeing lines or something to see or hear or like look at something.
This is the room where the light is on, and this is the room where the light isn't on. And over here it says you can only see black and white when it's dark, and here you can see colors when the light is on.
How we see is we use light because we can't see without light, and here the sun is reflecting toward the eye, off the eye, and the eye sees by looking at the tree, and then inside here it's upside down and then reflects back out, and you see it right side up. And then here I'm seeing the eye sees by looking at the tree with help by the sun for light. This is the sun, and these are light rays. The light rays are going at the tree, and then the light's bouncing off the tree. It's going into the eye like this. Then these light lines cross, making the tree look upside down at the back of the eye, which is called the retina. The retina has a nerve that's connected to the back of the brain, and the brain tells you which way the tree should be and how far it is, and it makes you see it good. And without light, you can't see anything because the light needs to bounce on an object, so it can go into your eye and into the back of the brain.
What I drew was, for an example, I drew a fish for the picture, and the sun is reflecting on the fish because I drew a little key here. It's like, this is kind of like a web here, and like the yellow one means sun reflection, and the red one means reflection to the eye. That means the reflection is going into the eye. I wrote sun reflects on the picture, so it's reflecting off of the fish and it's going into the eye. The picture goes through nerves to the back of the brain, and I put a dot where it goes to, and
you see it upside down, so it flips it right side. This is what it's showing it's doing. Flips it right side up, so your brain sees it as right side up.
Let's take a closer look at their posters. All the children said that we need light to see, but they didn't always make that connection in their poster. John imagines vision as looking out and then getting light back from the object. Crystal has the idea that the light from the sun goes to the eye and then from the eye to the tree. Shane uses the idea of seeing lines, which seem to come from the eye, almost like Superman's invisible rays. These seeing lines let us see objects. He also includes an interesting idea that air has colored particles in it that we see in the day. Deborah, Erin, and Chris clearly show that light from the sun is reflected from an object to our eyes. These children hold typical ideas of vision similar to early scientists.
In the year 965 AD, mathematician and physicist Alhazen was born in Basra, presently Iraq. In his lifetime, he created a new understanding of how we see. Prior to Alhazen, people believed our eyes emitted rays that made objects visible. He observed that when looking at light, such as fire or the sun, his eye would feel discomfort. This proved that the eye is affected by light. Alhazen also showed how light affects sight. If he was in a chamber with a wide opening exposed to the sky and light and looked at the opening for a while, he would find the shape of the opening remained if he closed his eyes or turned to a dark place. With these two experiments, Alhazen showed the relationship between light and what we see. Because of this and other extensive research, he is considered the father of modern optics.
Our colleague, Dr. Camille Wainwright, a science educator at Pacific University in Oregon, showed us a model of an eye that she uses with her students.
Eyes. We all know something about them. They have lids and eyelashes to maintain and protect the eye. In conjunction with the tear ducts, they keep our eyes safe, clean, and moist. They wipe away dust and tears similar to a windshield wiper. Another thing we can see is the color of the eye on the front of the white eyeball. The color portion of the eye is called the iris, and it comes in various shades of blue, green, gray, hazel, or brown. Regardless of the color, eyes have a black spot in the center of the iris. This is the hole through which the light enters the eye, the pupil. The cornea is the first optical component of the eye. The light is refracted as it passes through the cornea. The path of light continues through the pupil and then through the lens. When the light meets the lens, it is refracted further. It changes direction as it meets the front surface of the lens and refracts even more as it leaves the back surface of the lens. The lens in the human eye is remarkable. It actually changes thickness in order to focus the path of light. When you're looking at something near to your eyes, your lens must be very thick in order to focus the image properly on the retina. When you look at something at a distance, muscles pull the lens thinner so that you can focus on something far away. This is a very realistic view of the retina because we can see the blood vessels, which resemble the branches of a tree. We can see the fovea, which is the place on the retina where we have the sharpest vision. Notice there are no blood vessels in this area of the retina, but there is a concentration of detectors here. At this spot, there are many blood vessels, but no detectors. That's why this is called the blind spot. This is the place where the nerves collect into a single bundle called the optic nerve. It's the optic nerve which carries the vision message from the retina to the brain. We'll be looking at the function of the parts of the eye in more detail throughout this workshop.
Let's look at our own eyes now. If you're alone, look in a mirror. If you're in a group, pair up to do this activity. Look closely at the iris and the pupil of your partner's eyes, or look at your own eyes in a mirror. Now cover one eye and notice what happens to the pupil in the uncovered eye. If the pupil is just a hole, how does it change when you cover one eye? Why does it change when you cover one eye? What other function might the pupil have in helping us see?
A good analogy to the eye is a camera. The camera has a diaphragm which changes the size of the aperture, the hole in the front of the camera that the light passes through. This is like the iris in the eye, which changes the size of the pupil. Here we can see the diaphragm changing. When we want a photograph to show everything in focus, objects near as well as objects in the distance, we need a very small aperture. If we want to take a photograph of an object close to us, and we want that object in focus, but don't want the background in focus, the opening in the diaphragm must be large. We are talking about depth of field, the range of distance that is in focus. In the eye, the pupil changes size, not only to control the amount of light that comes in, but also to control the depth of field. The camera lens refracts the light so that the image can be focused. However, the camera lens is not flexible like the lens in the human eye. The image must be focused at the back of the camera where the film is located. The film absorbs the light energy, which is transformed to chemical energy. We've seen that the camera has some similarities to the eye, but the eye is much more complex. I visited Dr. Carl Sitek, a professor of optometry at Pacific University, for my yearly eye exam, and he took a close look at my eyes.
Do you see anything on the line below that?
It's a little fuzzy. ZKCZV.
Great. And now with both eyes, please.
ZKCSV.
Excellent. We did that as a test of your ability to see fine details. Okay. Now I'm going to check your eye movements. Do you see the little letter A right there?
Mm-hmm.
Okay. And just follow it with your eyes. Keep your head still and just move your eyes. We need to move our eyes because that area of the retina that has the clearest vision is only a very small part. So if we want to look at fine details, we need to move our eyes around. And we have to check that to make sure that you can move your eyes in all directions. Okay. I'd like you to look out at the distance, please. And here I'm going to check that your pupils are responding properly to light. Now the reason that we do that is to check that the pupils constrict and dilate properly. Now they do respond to light to control the amount of light that gets into the eye, but that's not the main reason why they work. The pupils control the depth of field of the eye, and what that does is it gives you a range of clear vision. So it allows you to see near and far without having to change focus.
So on one of my cameras, I have the ability to change the diaphragm to allow me a larger range of distance in which I can focus.
Yes, that's correct. It works exactly the same way. Okay, that was very good. Now we're going to check the health of the eyes with this instrument. And I'd like you to put your chin on the chin rest right there. And hold real still. I'm going to be videotaping this for later so we can take a look at it later. So the first things that we'll look at are the optical components of the eye. In the front we have the cornea, which is the clear window where all the light comes in. It actually changes the direction of the light, and it is the strongest of the optical components within the eye. And on the right-hand side of the image, we see the right part of the curved slit, and that represents the front surface of the cornea. Just to the left of that is the back surface of the cornea, and that's represented by that second curvature. The next component then is the lens. And the lens sits behind the iris, which is the colored part of the eye. That also makes the pupil of the eye. Now the lens has a front surface, which causes the light to change direction even more, and it also has a back surface. Now when we look from something far away to something close up, the lens actually changes thickness, so the focus of the eye changes. As we get older, the lens thickness increases, and we lose the ability to change the shape of the lens so that we can no longer focus from far to near. Now we're going to check the lens powers to make sure that we have the best possible correction for the glasses that we may be prescribing. We'll check the right eye first. So what I'd like you to do first is read the lowest line on the chart that you can.
DVOHC.
Very good. Now we're going to check the final refraction. I've got one line of letters out there. I'd like you to read that as soon as you can see them, even if they still look a little bit blurry.
I can see them now.
Good. Try for me, please.
HVZDS.
Does that look any better?
A little bit.
Okay. And what if I go one more step?
That's better.
Right. Okay, we'll hold it right there. Now I'm going to take a look at the back of the eye. And to do that, I need this additional lens to help focus the light more. So here we're looking at the retina, and I can actually see the fovea, which is the area of the clearest vision. And if you remember before from when we tested eye movements, when you were doing the tracking, that's the part of the eye that you have to move around to be able to see clearly. We can also see the blood vessels, and those blood vessels actually lie on top of the photoreceptors. And here we have the optic nerve head, which makes up the blind spot of the eye.
Here's another representation of the human eye. This model has some useful features that allow us to demonstrate the way an image is actually formed. At the front, the glass represents the cornea. I can add a part that represents the iris with the pupil in the center. Then I'll add a lens. And finally, water with dye in it to represent the liquid which fills the human eye. Although the liquid in the eye is a much more complex solution than water. In the front of the eye is a source of light. We can see the image formed on the back of the model, the area that represents the retina. Notice that the arrow in the light source points upwards, but the arrow on the image is inverted. We can clearly see the image on this model, but if we looked inside a human eye, we would not see an image sitting on the retina. That's because the retina has absorbed the image. It has literally soaked up light energy and converted it into the chemical energy and the electrical energy that carry the message to the brain through the optic nerve. In the human eye, the thickness of the flexible lens can be adjusted to focus light on the retina. But if the lens can't adjust sufficiently, individuals may need corrective lenses or glasses. A nearsighted eye is able to see images clearly when the object is near the eye. Notice that the path of light from the source is focused nicely on the retina. But when I move the eye model far away, the focal point is in front of the retina and the image is not in focus. However, this is easily corrected by wearing glasses. If I put an additional lens in front of this eye, this lens will spread out the path of light so that the lens inside the eye is now able to focus on the retina. Now let's look at a far-sighted eye. When the source of light is far enough away, the eye focuses the image very nicely. That's why this condition is called farsightedness. But when the eye is close to the source, the lens is not able to get the image in focus. One possibility is that the lens isn't flexible enough to thicken sufficiently. This happens to all of us as we age. But using reading glasses adds the extra thickness needed to refract the light so that the eye is able to focus the light on the retina.
Dr. Sittek and Dr. Wainwright showed us how light enters the eye and reaches the retina, producing an inverted image. As we've seen, the camera is a good analogy to the eye. Here we see that light from an object is refracted by the lens in such a way that the image on the film is inverted. Of course, we don't actually see the image on the film until it has gone through a chemical process known as developing. Earlier, we heard children accurately describing an inverted image of an object on the retina. But just like camera film, we don't see an image on the retina. Instead, light is absorbed by the detectors on the retina, transformed into chemical energy, which initiates messages in the optic nerve that go to the brain. So we might say the brain develops the picture. In classrooms, children can explore image formation using hand lenses. We visited children from Linda Holland's combination 3rd and 4th grade class in Lowell, Massachusetts, to watch their explorations. Children are familiar with the use of hand lenses to produce a magnified image of the object they're examining.
But when you look on the top, it looks like a bunch of mountains.
But if the object is far away from the hand lens, they can capture an image on a screen, such as a white piece of paper. Here we see the children produce an image of the trees that they see through the window. The image is upside down. The lens of the eye works in a similar way to this hand lens. inverting the light that lands on the retina.
I can see outside, and I can see the window.
Here's a simple model that shows how the eye works. We use a clear plastic dome for the cornea, some construction paper and paper fasteners for the pupil and iris. We use a plastic hand lens for the lens of the eye, and water in a clear plastic container with a little yellow dye added as the liquid in the eye. At the very back of the model, where the retina of the eye would be, we place a piece of mounted paper. Looking at the model from above, we can see the path that the light takes through the lens, the liquid in the eye, and onto the retina. We can clearly see the inverted image of the light bulb on the retina. When we open and close the iris, we can see the difference in the amount of light falling onto the retina.
Let's return now to Dr. Sittick and Dr. Wainwright as they look at the retina, the place where the light detectors are found.
Dr. Sittick, tell me about the detectors on the retina at the back of the eyeball.
Those photoreceptors that we're looking at, they're rods and cones. Rods give us our nighttime vision so that we can see in low light levels, but it's not very clear vision. Also, there's only one type of rod, so the only information that we get is about brightness. We can see different shades of light and dark, but we cannot distinguish color. When the light level gets bright enough, then the cones start to work. And when the cones work, the rods shut off. You know that your cones are working when you can see color because we have 3 different types of cones. One type is sensitive to low energy photons, another type is sensitive to high energy photons, and one type in between is sensitive to the middle energy photons. When those are working properly, they give us color information. The ones that respond mainly to the low energy photons see mostly red, but they do respond to other colors as well. The ones that have the peak sensitivity in the medium energy, those respond mostly to green, but again, they do see other colors as well. And then this final curve where they respond mostly to the high energy, those have the peak sensitivity in the blue region of the spectrum, but as with the others, they do respond to all colors.
I'm surprised to hear that. I usually think of them as corresponding strictly to the red region and the green and the blue, but you're describing it as a much broader spectral response than that.
Yes, it is much broader. They do have peak sensitivities in the red, green, and blue parts of the spectrum, but they do have sensitivity across the whole spectrum.
And those that respond to the low and the medium energy photons are really pretty close together in their sensitivity.
Yeah, those sensitivities are fairly close. And when someone is color deficient, what happens sometimes is that those peak sensitivities are closer together than they should be. So even though that person has all the cones, it's harder for that person to discriminate colors.
I see. So I suppose that if someone were colorblind, it would be because one or more of those types of cones isn't functioning.
That's correct, but we prefer the term color deficient because even though someone is colorblind, they can still see color, they just cannot distinguish certain types of colors. Usually what happens with males, because it's more common in males, is to have difficulty discriminating red from green, and those would be the low energy and the middle energy sensitive cones. Now, we said there was only one type of rod, but we can see at lower light levels with the rods.
So that would explain why in low light or in the evening we're not able to see color, but we might be able to discriminate light and dark because the rods are so sensitive.
Yes, that's correct.
So it sounds as though there's an analogy between the rods and black and white film in a camera and cones and color film.
Yes, that's actually a very good analogy.
Now we know that seeing color is really the result of cones receiving energy from photons with different energies. Photons themselves have no color. But are there colors that are easier to perceive than others? Let's see if we can find out. In this demonstration, we placed 3 colored filters on 3 desk lamps: red, green, and blue. Each lamp is connected to a dimmer. We shine each color onto a piece of white paper, making sure that all of the lights are at full intensity. Which color looks brightest to you? Our eyes perceive green to be the brightest, followed by red, then blue. We adjust the dimmer level of each lamp so that they appear to our eyes to be of equal intensity. Notice that now the green dimmer is lower than the red, while the blue is at full power. Our eyes are most sensitive to green light and least sensitive to blue light. You may have noticed that many emergency vehicles, like fire trucks and ambulances, are now painted yellow or green. This is because the human eye has its peak sensitivity in the yellow to green range. And that's not all of the visual information the eye has to interpret. From all the signals the brain is receiving from the eyes, it must interpret distance, movement, size, and color.
The brain processes a vast amount of information received from the eyes. But during this processing, the brain groups the information it receives into patterns that are sometimes incorrect. The result is an optical illusion. Artists have made use of the visual processing capabilities of the brain in their work. Pointillists such as Seurat produce paintings using thousands of tiny colored dots. When 2 different colored dots are right next to each other, your brain mixes them together with the effect that the dots are not distinguishable unless the viewer is close to the painting. Let's return to Michelle Sullivan's 4th grade class, where they've been doing some pointillist drawings of their own.
Boys and girls, remember that when you write your prediction, it's what do you think it will look like from across the room? What color will you see from across the room? You tell me. What does it say? Your prediction was correct, and then write down what you actually saw, okay? While you're waiting, if I were you, I might add a couple more magenta dots in the middle, because that might give you a different color. When you look at it from far away, you might want a few inside.
Magenta?
No, put dots in. Yeah, you can sit for a few minutes.
Say 20 or 30 or whatever, blue dots, and then you just double them.
Oh, nice job, girls. What do you see here, Joseph? Orange. Did you think it would be orange? You wrote cyan. So were you surprised? What about when you mixed your colors together and you wrote your predictions? Some of you were really surprised. I heard you say, "Oh, wow," when you were standing across the room from each other. How many of you had a different prediction than what you actually saw? Chris, what did you get?
I thought it would be blue because yellow doesn't show up as well as blue does. Right. So I thought it would be blue. Mm-hmm. But when I did the experiment, it turned out as a light green.
Can you see your paper? Oh, you're absolutely right.
How does it make a different color.
Marina?
Because it kind of blends in together, and so you see it.
Right. What color does Marina's look like? Christina?
Green.
It looks green to me too. Who says that looks green, the third one? Okay, good, nice job.
What happened with that one? Red and yellow trying to make a red for the lips and the signs on his hat. I tried to get the color brown for the stem, and I used red, blue, and green, and like.
Okay. Okay, Sonia?
I'm trying to get the red orange with. You put yellow in that blue, and you get the brown. For the purple, you put purple. I did a butterfly, and I put little holes in, like little circles, and in the circles I wanted it to come out green and purple, or violet. This came out green when I mixed blue and yellow together, but this kind of came out like a purple and a blue. Over here in the middle, I tried to make it brown, and I thought that magenta and black would make it brown because it looked like it in the paper.
I used magenta, cyan, and yellow for the stem, and that makes brown if you combine them all. I used yellow and cyan for the leaf to make green, and I used magenta for the apple.
I made a flower, and I overlapped most of the dots, and I used yellow and cyan for the leaves, and magenta and yellow for the petals, and I used yellow for the pollen. I drew a tree, and right here I used blue and yellow. I was trying to make wind, and right on the track, and I used yellow and magenta, and I was trying to make brown, and here I did the same, at the branch I did the same thing, and right here I did the same thing with the leaves.
Great job, you guys. Very well done.
Although humans' eyes respond to the light in the visible region, there are animals whose eyes are able to detect either infrared or ultraviolet light. And nocturnal animals have eyes containing many rods for good vision in low light. And have you noticed the placement of eyes of chameleons or zebra or birds of prey? Although humans perceive many hues of color, do animals? We visited the Franklin Park Zoo in Boston, Massachusetts, and talked with the staff about how some of the animals see.
As you walk around the zoo, and those of us who take care of the critters always notice eye placement's critical. This is an example of a prey species. Every animal's a predator, is predator and prey in some form, but what these guys prey on doesn't move. It's grass and foliage. You can notice that their eyes are on their sides. This is a species which needs great peripheral vision. Their eye actually bulges out a bit, in fact, and as you notice the live specimens, you'll see how that actually works. They have a great view around their body. This is a gorilla skull that gives you an example of eye placement very similar to our own. They're in front. They have excellent binocular vision, so that if they are climbing from branch to branch or jumping from branch to branch, and they're not going to fall off, It also gives them the ability to really interpret things close up. This is an example of a predator. This is a lion skull, and you can see the way that the eyes are placed again in front of the head. They'll have great binocular vision, great depth perception, but they won't have as wide a view as those prey items. Their eyes are placed towards the front of their head so that they'll know when to time their leap onto their prey.
Chameleons are completely diurnal. That means they're active in the daytime and not at night. And also color is very important to them, and colors are something that's very hard to pick up at night. So their vision is strictly geared towards daytime seeing full color. These two large domes that surround the eyes, those actually allow the animal to operate its eyes independently of each other. The left eye can look off in one direction while the right eye is looking in another direction. And they are also able to take both eyes and focus them towards the front and get an overlapping field of vision, which gives them that high stereoscopic vision, which is so important to them.
Thelma is a great horned owl. A great horned owl is a bird of prey, and being a bird of prey, she has binocular vision. We think that owls are more or less colorblind. Thelma would have more rods because cones are the things that help us perceive color. And since Thelma is active at night, she wouldn't need those. In fact, Thelma could see by the light of just one candle if it were held 4 football fields away on a totally dark night.
A lot of invertebrates or insects can actually see infrared. It's something that when we look around, we don't even know it's out there, but there's infrared and there's ultraviolet light that is active in our environment. It provides another means for these insects to find food sources. Animals' eyes have evolved to meet the needs of their interpretation of their environment.
Today we looked into our eyes, literally. We see because light is reflected from objects into our eyes. The optical components of our eyes refract the light so that we see things in focus. We illustrated how detectors in our retina absorb light, which allows us to perceive all hues of color as well as black and white. It is clear that our eyes detect the light, and in conjunction with the brain, we are able to see. Next time, we'll look at how plants interact with light.
See you then.
Don't forget to check out our website for additional information, activities, and discussions with your colleagues. The address is www.lerner.org/channel/workshops/shedding-light. And if you don't have access to the web, you can share your thoughts with us by email, fax, or regular mail. Our email address is channel@lerner.org, and our fax number is 617-496-7670. Finally, our mailing address is the Annenberg CPB Channel, Smithsonian Astrophysical Observatory, 60 Garden Street, Mail Stop 82, Cambridge, Massachusetts, 02138.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.
Hello everyone, this is Mayor Al Adam with an update. I'm here, safe at home with my family, and we hope that you're doing the same. Yesterday, Los Angeles County made the decision to close their beaches and hiking trails, and with the potential for too many visitors from Los Angeles to our trails, Conejo Open Space Conservancy Agency had to make the decision to close our trails as well. This is not the outcome that we wanted, of course. However, there are alternatives. Let's walk our neighborhoods instead, but please distance yourself when you do so. There are 82 confirmed cases here in Ventura County. We actually have 2 at University Village right here in Thousand Oaks, and I'm sad to say that we have had 3 fatalities. Los Robles Hospital has a few patients there. However, we don't want to overwhelm our hospital, so if you're exhibiting moderate symptoms, please call your primary care physician first before visiting the emergency room. Los Robles Hospital will be sponsoring a blood drive. That's this Wednesday and Thursday at 2190 Jans Road. It will be from 7 a.m. to 9 p.m. You can visit bloodforlife.org for information on that program. Food Share, which is our county regional food bank, will be delivering food to residents of Thousand Oaks on April 2nd. You can visit foodshare.com/COVID-19 for information on that program as well. And naturally, we want our seniors to be protected during this tough time. Senior Concerns is doing a great job with Meals on Wheels. If you want to help, go to seniorconcerns.org where you can donate or volunteer your time to make these deliveries. Ladies and gentlemen, the city is running well. Police and fire are there for your protection. We have a virtual library at your disposal, and you may notice that some construction projects are still running throughout the city. If you do have any concerns or you need our help, please feel free to call us at any time. We're there for you. And in the meantime, let's exercise our civic duty. Let's stay apart. Let's use distancing. It's the only way to stop this virus. We're in this together. I wish you all well, and I'll be back with another update shortly. Thank you very much.
Hi, I'm Dr. Jay Butler, Deputy Director for Infectious Diseases at CDC. I'd like to talk to you about the new virus that causes the disease COVID-19. Older adults and people who have severe chronic medical conditions like heart, lung, or kidney disease, or diabetes may be at higher risk for severe illness from COVID-19. If you are one of the people at increased risk for serious COVID-19 illness, it's especially important for you to take action to reduce the risk of getting COVID-19 now. The first thing you can do is take care of your own health. Wash your hands often with soap and water for at least 20 seconds. Use an alcohol-based hand sanitizer with at least 60% alcohol if soap and water are not available. Cover your coughs or sneezes with a tissue, or cough or sneeze into your elbow, not your hands. Avoid contact with people who are sick. Clean and disinfect surfaces in your home, such as counters, tabletops, and doorknobs, to remove germs. Use household cleaning sprays or wipes according to the label instructions. The next thing you can do is make a plan for what to do if you do get sick. Know who will take care of you if your caregiver gets sick. Talk to your healthcare provider about getting extra necessary medications to have on hand. Get enough supplies too, including enough household items and groceries so you can stay home for a few weeks if you have to. The third thing you can do is pay attention to what's happening locally. If COVID-19 is spreading in your community, stay home as much as possible and avoid crowds. If you get sick with fever, cough, or shortness of breath, call your healthcare provider. If you develop warning signs, such as difficulty breathing, persistent pain or pressure in your chest, confusion, or blueness of the lips or face, these may be signs of serious illness. Call 911. For more information and the latest resources, please visit cdc.gov/COVID-19 or call 1-800-CDC-INFO. That's 1-800-232-4636.
Good morning. You're seeing this video rather than a press conference because Ventura County wants to practice social distancing. We want to practice what we preach. A press conference brings too many people together in a close space. We're now seeing community transmission in our county. Community transmission means that people, much like when flu is transmitted from person to person, are becoming infected, and it's not clear where or who the infection is coming from. COVID-19 is spreading. We first saw it spread across China, and then across the rest of the world. Then it came to the United States, and now we're seeing it across Ventura County. We could see a doubling of the number of cases in our county every week. Places that are not responding aggressively to this virus are seeing a tenfold increase every week. Our response in our county is an aggressive one. We're going to ask you to stay inside for your health and for the county's health. We believe, and experience tells us, that this will result in a lower peak in the number of cases in our county. We're hoping that we'll start to see a decrease in about 6 to 8 weeks. We're aiming to have a lower bump of cases rather than a higher peak. This expectation is based on watching other countries and how the COVID-19 virus responded to those countries' similar aggressive measures against the virus. During this time, various venues will still be open. You'll still be able to go to grocery stores, coffee shops to take your coffee to go. You won't be able to congregate at the coffee shops. You'll be able to go to farmers markets where you'll see social distancing practiced. Restaurants will be available where you can pick up food, and wine shops and breweries as well, where you can purchase bottles to go. You'll be able to leave your home to exercise. This includes running, walking, biking, and hiking. You can do this by yourself or with members of your household. You'll be able to go to and from your doctor's office. You'll be able to walk around the house, including going outside to garden, and you can leave the house to pick up products for your pets. Essential businesses will remain open. I want to stress essential businesses. Those businesses will be asking some of their employees to work from home. Working from home distances people from others and opens up space at the workplace for social distancing. Workplaces will be maintaining 6 feet between employees. All aspects of agricultural production will remain open as well. If you're sick, do not go to work in those essential jobs. If you encounter someone when running an errand to the grocery store or other location, maintain a 6-foot distance from that person, especially maintain that distance if they appear to be ill. Be generous with those things that you have that you can share and drop off at their place. We will all come through this together. Ventura County is a county that